Welcome back, and going forward we are going to be doing things a little bit different. So far we've worried about circles, we've worried about triangles, but now let's just worry about trigonometry. Right, now that we've gotten the basis on how these things are defined, let's move away from how they're defined and just start using trigonometry. So to do that, what we're going to start with is we're going to start looking at just general trigonometric expressions. Not quite law of sines expressions, not quite law of cosines equations or anything like that, just general expressions. So remember for me, if you would, that a expression is just any statement in mathematics. They can be very, very simple in nature. 6 plus 7 is an expression. Obviously that simplifies a little bit. 1 over x minus 16yz is an expression. What's x, what's y, what's z, you ask? Well, they're just variables. They're placeholders. There's no restriction on what x, y, or z could be. We haven't specified anything about them, so they're just general variables right now. Another expression we could have would be sine squared of t times cosecant of t minus 2 tangent t cosine t. That's an expression. Right, we now know what sine is, what cosine is. We know how to evaluate those for all inputs, well, all real valued inputs. So these are legitimate expressions. And going forward, not quite this video, but immediately after this video, we will start taking one trigonometric expression, taking a second one, and saying they are equal, that they're different ways of saying the same thing. For instance, 6 plus 7 is another way of saying 13, right? Those two are equal. So going forward, we'll worry about equations, but for now, let's just worry about expressions, because we'll see that there's enough in there for now. So we have an expression here. We have a trigonometric expression. And if I were to ask you to evaluate that expression when t was 0, could you do it? And if I asked you to evaluate that expression when t was pi over 6, could you do it? Or when t was 150 degrees, could you do it? Hopefully the answer is yes. Hopefully you realize that you can put in those values, be they radian measure or degree measure, and use appropriate methods, be they the unit circle method or the right triangle approach, to evaluate each of those trigonometric values, each of those trigonometric expressions, and produce the overall value for sine squared t cosecant t minus 2 tangent t cosine t. Obviously, it would be a little bit of computation heavy, because you have to do the sine, you'd have to do the cosecant, you have to do the tangent, you have to do the cosine, and then you have to multiply all those things together, add them together. There's this -2 scalar factoring in there somewhere along the line. There's quite a bit of computations to be done. Well, just like how 6 plus 7 simplifies, so too can we simplify trigonometric expressions. And that's going to be what we're going to do right now. So how would you simplify this guy right here? How would you simplify sine squared t cosecant t minus 2 tangent t cosine t? Well, what comes to mind for me, one of the very first things I do, and in fact, when I don't know what else to do, this is what I fall back on. I rewrite everything here, all my trig functions, as just sines and cosines. Right? Because cosecant, that's 1 over sine. Tangent is sine over cosine. So let's see what we have and go from there. So if I were to simplify this thing, what I would do is first of all write cosecant is 1 over sine. Write tangent is sine over cosine. And then wait a minute, I've got sine squared over sine. Well, whatever number sine comes out to be, with one exception we'll get to in a second, but with everything else, sine over sine, that cancels itself out. So sine squared t over sine t, that's just sine t. And then for the other term, I've got sine over cosine all times cosine, so the cosines will cancel. Right? For whatever number cosine comes out to be, again with one noticeable exception, we'll get to that, cosine over cosine is 1. So after I cancel out my trig expressions, I've got now sine t minus 2 sine t. Well, that reduces down to just be negative sine t. And so if I were to ask you again to evaluate this expression at t equals 0, or t equal pi over 6, or t equal 150 degrees, Yes, we could do it for all this, or equivalently, we could do it for negative sine t. They are exactly the same. We have shown that these are equal expressions because we have simplified from one and got to the other. Now, the exception I mentioned, right? This first expression here is undefined at places, right? When sine is 0, then this first term is undefined. When cosine is 0, tangent is undefined. So that makes me undefined at 0, at 90 degrees, 180, 270, and so on. Not the case for negative sine t. Negative sine t is defined everywhere. So that is the one exception we do have to handle. We do have to mind when our original expressions is undefined versus the other one. But we will worry about that in turn. We'll take a few times getting more and more acquainted with that. But for now, let's not worry about that. Let's acknowledge it, however, and move on. Because what I want us to see right now, above all else, is that yes, we can just work with any expression in the universe, but it's oftentimes more in our interest to simplify before we work with it. Give you another example here in a second. First, though, I want us to have these things at the ready. Right? I want us to remember that if we're going to write things in sines and cosines, we've got to remember how. Tangent, sine over cosine. Cotangent is cosine over sine. Cosecant is 1 over sine. Secant is 1 over cosine. And we also have the Pythagorean identities. We might avail ourselves of that, right? That's existing knowledge. And that's not something you will ever have to memorize in this class anyway. And also the even-odd properties. We have access to those as well. And we might use those as well to simplify our expressions. So, as promised, the example. Suppose I wanted to simplify the expression sine cubed x secant squared x plus sine x. We can do that. And we might want to do that because that's a lot to look at, right? If I were to compute this, I would have to find a sine, cube it, find a secant, square it, and then take the sine again, multiply all that, add it. There's quite a few operations to be done here. Alternatively, I could first write the secant as 1 over cosine squared. And so I'm looking at sine cubed over cosine squared. That's sine times tangent squared. I've got plus 1 sine over here. I could factor out the greatest common factor, leaving me with this expression here, which is equivalent to what we started with. And this guy is, in turn, equal to sine times secant squared. Reason being is tangent squared plus 1, that's secant squared. That's our Pythagorean identity. So we can actually reduce this mess into just be either sine times secant squared, or if you want, tangent times secant. This might be preferred because it's one less operation, right? I'm not having to square anything. But those are both fairly nice and fairly simple, especially in comparison to what we started with. And I've said it before, I'll say it again. Some degree of familiarity with fractions is going to be required. Right? Because transforming this into sine times tangent squared does take a little bit of realization. But it doesn't stop there. I got one more I want us to look at in this video. And it's not a pretty one, but it will clean up nicely if we do the right steps. Yeah, it's all that. But anyway, I've got the expression tangent of theta plus cosine theta over 1 plus sine of theta. And I want to reduce that down. And the reason for that is fairly straightforward. That's a lot to look at. So how would I do that? Well, I've got essentially two fractions. And that's not clear immediately, but it is clear once we rewrite tangent as sine over cosine. So I've got one fraction here. I've got one fraction here, and they're being added together. In order to add fractions together, they have to have the same denominator. And the lowest common denominator between cosine and 1 plus sine is just the product, cosine times 1 plus sine. So the first fraction I need to multiply by 1 plus sine. Of course, I need to do that to both top and bottom. Also, for the second fraction, having denominator already of 1 plus sine, I need to multiply by cosine, top and bottom. So that produces, after I do a little bit of writing, after I add everything together, sine theta plus sine squared theta plus cosine squared theta. That's my numerator. My denominator is cosine theta times 1 plus sine theta. And you could distribute that out, but as you see almost immediately, you don't want to. Because sine squared plus cosine squared is always equal to 1. That, again, is the Pythagorean identity. So in my fraction, I've got sine theta plus 1 in the numerator. I have a factor of 1 plus sine theta in the denominator. Those factors cancel, leaving me just with 1 over cosine theta. So if you were to have to compute tangent of theta plus cosine theta over 1 plus sine theta for varying values of theta, go for it. You could take theta and you stick that into this expression, do all that mess, or just find the secant. These expressions, these two expressions, secant of theta and all this stuff over here, those are different ways of saying the exact same thing. So would you rather say the short version, or would you rather say the long version? And that's the immediate takeaway from simplifying expressions. We want to take something that is convoluted and complicated and takes a lot of computations to evaluate and turn it into something more straightforward, more direct, easier to look at, easier to work with. And that's what I want us to do right now. That's what I want us to do as we get back into the swing of things. So, a few last tidbits for you to hold on to. There's more than one way to simplify things. If you were to look back over these examples, you could probably find other ways to simplify them. And you might not actually end up with the same expression at the end. It might be just a slightly different, but ultimately equivalent expression. But in simplifying, hoping that I've got you invested in the process of simplifying and the reasons for it, here's some ideas on what to do as we go along. One thing to try is list everything as sines and cosines. That might be the first thing we do, and if all else fails, that might be the last thing we try. It always can help. Other things we might want to hold on to is we can use existing identities. Currently we have the Pythagorean identities at our disposal. We also have the even-odd identities. But we will add more and more identities onto that list as we go. Also, as we just saw here, another thing that might help is combining any fractions we have into one single fraction. If nothing else, doing that reduces the number of fractions we have, so in that regard it's simpler. But there might be other benefits that happen as a consequence of combining fractions. And that's what we're doing here. That's how we're kicking off this half of the unit. So, in class next time, we will look at expressions with trigonometric bits in them, and we will clean them up to the best of our ability. So let me know what you're worried about. Hope it goes well in the class. We will start doing things in there. And then after this class, for the next set of videos, we will start looking at trigonometric equations, specifically identities. So I look forward to that part. I will see you then. Have a good one.